So it's my great pleasure that we are able to have Roy Feinstein here with us today. He calls the DC metro area home. He originally came from South Africa, and he earned a degree in photographic science and visual communication. Definitely a background that shaped his broad interest over the years and really drives where he's had his invention and impact areas. Roy has designed graphic and scientific software applications that have had significant intersections with the work we do here at NIST. His company, Double Take Images, has developed a video analysis system that assists law enforcement in the enhancement of videotape and film, and it's currently being used by California law enforcement. Roy also holds a patent from 1988 that's the foundation of predictive text, the software that interpreted what word you were trying to spell out on the phone or keypad. The days before we all had smartphones with QWERTY keyboards. And perhaps what Roy is best known for is his pioneering the art form of impressionist mosaics. That's artwork composed of hundreds or thousands of images of stone tiles using the natural flaws and marbling to create an image. And so he's used this technique to generate artwork from mosaics of other images or photos. He's a very renowned artist. He's been commissioned for a number of big events to celebrate the 50th anniversary of the Grammys, and as well as to the 50th anniversary of Disneyland and Disneyland California Adventure Park and state of Hawaii. And I was looking online at some of his mosaics that he did for Disneyland, and I had just been to Disney World last week for spring break with my kids, and I think you missed one kind of vital image, which would be people standing in lines for hours, but maybe next time. So further example of Roy's really broad and Renaissance-like breadth of interests and talents are he's authored several books focused on evolutionary underpinnings of human behavior. From The Animal in You, which explores the biological reasons for why people tend to act like different animals to some degree, to The Secret Universe of Names, which looks at how meta-effects of how sounds influence human behavior. And today he'll be speaking with us on his latest thinking on animal and human behavior, centered on the mechanism of animal vision. And so we at NIST will be able to relate to the source of Roy's first thoughts on the subject, a software glitch. So many breakthroughs in research, originate from a mistake or a chance finding. And so, having the creativity to turn that unexpected outcome into an ingenious new theory is really a powerful thing. And so please join me in welcoming Roy Feinstein to NIST and give him a warm round of applause.
Hi, Jason. Thank you very much for the introduction. And NIST, thank you very much for having me here today. I'm going to try and get my talk going here. Okay. I've called my talk The Zebra's Stripes because it addresses one of the enduring biological mysteries that really has no satisfactory answer. Biologists have always felt that the zebra stripes are a result of camouflage purposes, or perhaps to confuse tsetse flies, or to allow foals to find their mother in a huge herd. Unfortunately, none of these theories are particularly satisfying, and this is one of those questions that have sort of been pushed aside by biologists because there really is no satisfactory answer. What I hope to do today is answer that question, and in order to do so, I have to present to you a brand new theory of animal vision, and my goal is to change your mind on everything you think you understand about how animals see. And at the end, it's provocative, and I'm hoping that the questions and challenges that come from this audience will take it on. The first thing to understand about vision is that it's not really a function of the eyes. Vision is really a brain function. It's the brain's attempt to create a virtual representation from the two-dimensional images that fall in our retina. It's quite a challenging task. So if you imagine, we look at a scene, we have two-dimensional images on our retinas. The brain has to then create this model in our brains to sort of hopefully represent the real world. It does this through a number of shortcuts because the process is actually very technical and difficult. And a good illustration, A good illustration of how sometimes these shortcuts don't work is this well-known Adelson illusion. If you take a look at the squares marked A and B, they're very clearly two different shades of gray. But in fact, this is a trick that your brain's playing. And if I remove everything from the scene, with the exception of those two squares, you'll see that they're actually the identical shades of gray. Now, even if I go back to the original, intellectually, you know they're the same, and yet your visual system keeps insisting that they're differently colored. So you have to be careful of interpreting what you see. What you see always isn't reality. Now, one fundamental of vision, and a very important aspect of it, is called shape identification. The ability to look at the outline of an object and identify it either as friend or foe. This is such an important component of animal vision that it's been established that even baby goslings, from the time that they're born, have these shapes already imprinted in their brain. So a newborn gosling will come out of its nest. If an eagle flies over, the gosling will duck. If it's its mother, it'll actually rise up and greet it. So a very important function of animal vision. But before the brain can discern these shapes, it has to pull these shapes out from the background. And some of you might be familiar with this process. It's called edge detection, the ability to separate the edges of an object in a scene. Now, this is actually quite a complex task. And if you look at the formula below, this formula has to be applied to every pixel in every frame at 30 times a second as it moves through. With those expensive square root calculations, this can put a lot of strain on any kind of processor. In fact, artificial vision researchers tend to get bogged down by this because there are so many calculations that have to be made every second. Certainly, this is a challenge for a brain as well. Now, human beings have evolved a gargantuan brain compared to those of animals. If you compare it, say, to a mouse, it's on the order of 1,000 times more volume. And we use almost 40% of our gray matter just to process vision. That's a huge amount of processing power. And the question arises, for us to see the way that we do, it takes an enormous amount of gray matter. How on earth could a mouse or a cat or even a fly see as well as we do? Certainly, they don't seem to have any problem. They can hunt, they can fly around at full speed without bumping into objects. And yet, there must be something that they were giving up. This is another one of those biological questions that really hasn't been satisfactorily answered. So let's discuss the possibilities of what maybe they could be giving up in their vision. The first suspect is maybe they just see the world in much lower resolution, sort of this blurry, low-resolution world. But we found that animals actually, in many cases, have better acuity than we do. They can resolve two separate points much finer than we can. In terms of visual field, animals actually see more than we do at any one moment. So again, there's more data that they have to process. When it comes to depth perception, we find that animals, with the possible exception of this one, can actually see in 3 dimensions at least as well or better than us. And when it comes to sensitivity, clearly animals like cats and dogs can see better in low light. So we haven't found any overhead savings yet. Perhaps it's got to do with vision, color vision. Now, human beings are trichromatic, which essentially means that we can see the entire color spectrum quite well. Cats and dogs do have a truncated version of that. They tend to see more in the greens. Snakes, on the other hand, are very much towards the red end of the spectrum, including the infrared. And birds, such as birds of paradise and parrots, are what's called pentachromatic. They actually have a much better color spectrum than we do. They can pick out hues that we are unable to do so. And significantly, and we're going to talk about this a little later, birds of prey, like hawks and owls, raptors, they tend to see mostly in the greens. And the reason, if you can actually look at a bird and decide what their color vision is by looking at their plumage. Birds with wide spectrum ability tend to be brightly colored, whereas raptors and owls tend to be brown and gray. And finally, there's an aspect of vision called flicker fusion rate. Flicker fusion rate is defined as the frequency of still images that we need to see in order to create a continuously moving stream. So kind of like looking at a movie. Human beings, our flicker fusion rate is 30 frames a second, which means if we watch a movie at around 25 to 30 frames a second, we see a continually moving object. Predators, on the other hand, like dogs and cats, actually see at 70 frames a second. And houseflies, with their tiny, tiny brains, actually take in information 300 frames a second, which they need to do because they live in a world of fast-moving tails and fly swatters, so they can't afford to miss a single frame of activity as they go. But this is counterintuitive, because it seems on the surface that if information is coming in at 300 frames a second, the amount of data could be overwhelming. I mean, we see at 30, they see at 300. So this is the mystery of what animals give up is actually deepened. So now I want to tell you about an incident that happened a number of years ago when I was working on some forensic video software. I had filmed this ruler, for reasons I won't get into, being pulled by a piece of string, and I ran it through my processor, expecting a certain result. What I got back was a very strange result that looked something like this. And this, obviously, I realized I had screwed up somewhere, but I wasn't quite sure what was happening. On a hunch, I did the same thing. This time I put a black mark running parallel to the direction of movement and ran that through the processor. And I got something identical to what I'd seen earlier. So pursuing this further, I wrapped some tape at 1-inch intervals around the ruler, perpendicular to the direction of motion, and I got that. So now I thought, this is very interesting, that objects that were perpendicular to the course of motion showed up, objects that were parallel to it didn't. What was actually going on is something that I call delta processing. What the software was doing was, it was looking at each successive frame of the video, and where a pixel had changed in value from one frame to another, that was rendered onto the new video. If nothing had changed, nothing was rendered. So in this example of this dog wagging its tail, you'll see that the tail, only the tail is visible, as well as that patch of green grass behind the tail, which also changes from frame to frame. So this is delta processing, and it's going to form the foundation of this new theory of animal vision. I came up with a hypothesis that perhaps what animals are actually giving up in their vision is everything. That animals actually see nothing except for things that change in their visual field. Like I said, it's provocative because I'm essentially accusing animals of being blind most of the time. So how would that work in the real world? How could animals function, hunt and escape and navigate under those conditions? Here's a frame from a video that I shot back in California. I had climbed onto the roof where the seagulls tend to nest. I wanted to see the world from their perspective. And this is a single frame from some video that I shot. Now, this is actually a very complex scene. If you look at it, there's 4 groups of people, there's lens flare, there's shadows, there's trees, there's trash cans. There's a lot going on. And if you've got a brain the size of a seagull, it can be quite overwhelming to sort of keep track of everything. But this is what I believe the seagull actually sees. You'll notice that everything has dropped away. And more importantly, that issue that we discussed earlier of edge detection, that complex mathematical formula that's required to pull things from the background, these edges have now been perfectly rendered without the use of any mathematical formula. This is just a simple filtering technique that requires almost no computer overhead and therefore no brain overhead. And more importantly, the objects that are most important to the seagull, such as the person closest to the gull and walking the fastest, is rendered more heavily than objects further back. If you look at the people in the top right, you notice they haven't even rendered at all. So from the seagull's perspective, they're not a threat, and therefore the brain of the seagull doesn't have to even contemplate their existence. But I noticed a problem. This was the result that I was getting initially. I was hand-holding the camera, and those little tiny movements that I was having were causing pixel changes on every pixel in the picture. This is an intolerable situation for a brain. Even we would have problem trying to decipher who's what and what's going on. And I was wondering if possibly nature had a solution for this. And it turns out that it does. This is actually a very deeply embedded component of all animal behavior, and that's vision stabilization. So here's a man moving a chicken in all different axes. And you notice that the chicken manages to maintain its vision fixated on a certain spot. We notice this in the classic example of a cheetah running at 60 miles an hour. It's just beautifully stabilized and fixated on its prey. Birds do it as well. And for birds, this is very important because when an eagle is floating a couple of thousand feet in the air, buffeted by winds, and it's using its telescopic foveal vision, it needs to stabilize that even more. Some researchers even attached some sensors to a fly's head. And as the fly zipped around the room, sort of landing on the ceiling and doing little twirls and arcs, they found that it could instantly move its rostocordial axis around its head, keeping its vision stable on any particular point. So flies do it, birds do it, we all do it. In fact, it's the reason we can read in a car. Even if the car is bouncing up and down, we somehow stabilize our vision on the tiny words in the newspaper, and we can actually read. Somebody pointed this out to me, and it kind of puzzled me for a while. If this is true, then why does the pigeon bob its head as it walks along? I mean, it seems to fly in the face of it. Turns out, a couple of decades ago, some scientists figured out that in slow motion, the bird stabilizes its head until the rest of its body catches up, jerks it forward, and keeps it stable. So wherever you look in nature, you'll be surprised at two things. One, how well animals stabilize their vision, and how well and how much time they spend in frozen situation. And we'll get to that in a second. Finally, that flicker fusion problem that I discussed earlier, that the fly is seeing the world at 300 frames a second, starts to make sense in the light of this delta vision. So in an example of this frog leaping quite quickly forward, a fly with 300 frames a second flicker fusion rate is actually going to see less data than an animal with a slower fusion rate. And the reason is that the differences between two successive frames will be less the faster those frames move. So there's less data. In this instance, the fly could easily shape detect the frog. It has very little other information to go by, mind you. It doesn't know what species the frog is, but it doesn't care. All it knows is that it's a frog, it needs to get away. A dog, on the other hand, with a slower fusion rate, would see more detail. In this case, maybe look at the markings and the camouflage and determine maybe this is an edible frog. And that's significant. When I realized that the flicker fusion rate was actually providing less data, everything started to fall into place. So I began to look at other animal behaviors, looking for evidence for my theory. And one of the most striking ones I came across was something called serpentine motion. It's a very distinctive movement. Snakes move kind of in the way that a string would when being pulled through a hose pipe. So if you imagine a curved hose pipe, the string moves through that hose pipe. In a sense, the snake's body is passing over the path laid down by its head. So it walks in its own footsteps. Snakes are unique in that 85% of them are non-poisonous. They have no arms or legs. They are completely defenseless. The only defense they have is their ability to remain hidden through their particular kind of motion. So let's look at this video of a black snake sort of moving across the grass, not so easy to see, and preparing to strike. Through the delta vision, a potential predator would not see anything about the snake except for the portion of the head that changes as it moves across the grass. If, however, we get a striped version of the snake, as we saw earlier, we actually see the entire snake as it moves across the grass. So why would a snake want to be seen? Well, clearly, poisonous snake wants to advertise its position so that it's not accidentally picked off by a bird. I then found out that there's really three basic color schemes to snake. There's the monochromatic snake on the left, the longitudinally striped snake in the middle, and the banded snake on the right. Almost all non-venomous snakes are either monochromatic or longitudinally striped. And as we saw, they're both invisible under delta vision. The only one that shows up tend to be the venomous snakes. And of course, there are some non-poisonous snakes that mimic venomous markings, but that's another story. So this is just a summary. Non-poisonous snakes do not show up. This is also why I believe that there's a differential between the juvenile and adult coloration of certain species. In this tree viper, for example, when the snake is young and hasn't really figured out the world, it wants to remain invisible to predators, whereas the adult then starts to take on the distinctive markings you see on the right. Some snakes have even figured out the best of both worlds. When this snake is crawling along the grass, it would be invisible to everything, and the only time it wants to be seen is when it raises to strike and threaten a potential predator. I came across this, and this to me was a fascinating little sojourn that I took. This is a very common marking for snakes, this red and black coloration, but it's always associated with non-poisonous snakes. And I was wondering why a red-banded snake like this would be colored this way, because as it moves across the grass, it's very clear, as everything we've seen, that it would be highly visible. Then it hit me that from its primary predator's point of view, which are raptors, raptors' color vision is centered around the green end of the spectrum. It's exactly like looking at the world through a green filter. In this case, the green filter would absorb all colors, especially the red, and turn them black. So you'll notice that the red stripes have turned black, and along with the pre-existing black stripes, the whole snake is now monochromatic. So from the raptor's point of view, this snake is fundamentally invisible throughout its length of motion. I thought, wow, that's very clever. So the snake has figured out the evolution has figured out a way to hide the snake from its predator. But why go through all that trouble? Why put the stripes there in the first place? Why not simply make the snake brown? And then it hit me that this snake has other reasons to have these markings. From another snake's point of view, a potential mate, for example, who see the world as if through a red filter, the red stripes now turn white and are perfectly contrasted against the black stripes that already exist. So from a potential date, the snake is highly visible. So this is an example of coloration that's both triggered by sexual selection as well as predatorial selection. I think it's the only example, at least that I've come across, where somebody's markings have two separate benefits. You'd also expect that if animals can only see things that move, you'd expect to see this kind of behavior in other aspects of animal behavior. Have a look at this common house cat. Hasn't been trained in any way. This is an instinctive behavior, and is playfully stalking the photographer as it goes. And watch how little movement in the cat until the cat gets very close to the photographer. So the photographer's going to hide off screen briefly. And you see this kind of behavior in the wild, where predators will synchronize their movements with that of their prey to essentially disguise their approach. This is the reason that freezing behavior is so universal. The classic example of a deer frozen in headlights. To us, it doesn't really make much sense to our vision. We can walk up to a deer at night with a flashlight, and the deer freezes, and we're going, well, we can see you. Why don't you run away? But the fact is, this freezing behavior is universal. Human beings do it. We talk about being frozen in fright. And certainly if we're alone at night, we will also freeze, sometimes involuntarily. It's carried to extreme examples. The classic case of a possum playing dead is a form of freezing that we call tonic immobility. And this tonic immobility is pretty universal. It happens with goats. It can happen to rabbits, even pigeons under extreme stress, and when in absolute fear, human beings as well. So the question comes, if animals can only see things that move, how on earth can they navigate in a world of non-moving inanimate objects? Why don't we see more of this kind of behavior from animals? The answer is that when you move, you create changes in the environment, perspective changes. So if we look at this video from a dog's point of view moving through a field of chess pieces, and we show it through the delta vision, look at how beautifully these chess pieces are edge detected. And you'll notice that the objects closest to the animal are rendered much more sharply than those further back. This is important because the animal's foveal vision, the part of the vision that's going to analyze what's up, needs to be able to focus in on the objects that are most important, which are the objects right in front of it. If you're a horse running through the jungle and there's obstacles right in front of you, they are far more important than the ones maybe 10 yards away. And this is how I believe it all fits together, is perspective changes faster when you're close than it does when you're further away. Okay, now that we've gone through this whole long explanation, we're going to get back to the zebra. How does this all explain the zebra's stripes? In order to do that, let's just look at the nature of the zebra. Zebra are extremely dangerous animals. Their hooves can shatter a lion's jaw. They're the only ungulate in the world that uses its teeth as a weapon. They outweigh the lion. They're faster than the lion. Very aggressive, very powerful animals. They're not to be taken lightly. From the lion's point of view, when a lion decides what to eat, when it has a choice, it uses a formula that I've sort of summarized at the top there. It looks at its choices and it says, what are my chances of successfully catching the animal, multiply by the amount of caloric reward that I'll get, and I divide that by the risk of injury to myself. Lions can actually do math, by the way. All animals do a lot of higher math, but that's another story. In this case, the carcass on the left has a high degree of nutrition with 0 risk of injury to the lion and obviously 100% chance of success. So, which is why lions are primarily carrion eaters. The only time they hunt is in the absence of carrion, and then they use this calculation to choose which prey to go for. So, confronting a herd of zebra and using that formula, the lion has a problem. These are very dangerous animals, and it needs to lower its risk of injury. The way to do that is to select an injured, infirm, young or old or diseased animal from the herd. Lions are very good at picking out slight changes or limps in gait, and they'll spend a lot of time hidden in the bushes just watching and looking for that weakest animal. Now the lion has a problem, however, that once it's made its choice, in this case the second one from the end, the chase begins. The lion is now going to run at 30 miles an hour, hooves are going to be flying, dust is in the air, very low contrast situation, a lot of confusion. How is it going to be able to keep its lock on that particular individual? And thanks to the zebra's stripes, and this is an actual frame from a chase, you'll notice that with all this low contrast, difficult environment, the stripes of the zebra have somehow, well not somehow, they have very clearly delineated each individual zebra. The lion cannot help but keep a lock on its chosen target. In fact, if you look at the way the stripes of the zebra are designed, take a look at the torso, the vertical stripes in the torso. These are moving perpendicularly to its motion. As we saw, that shows up well in animal vision. If you look at its legs and forelocks, those stripes are horizontal. Those legs are moving up and down, also perpendicular to the motion. The rump, which is a combination of both, are nicely conformed at 45 degrees. So the zebra is actually working very hard, the zebra stripes, to allow the animal to lock in on its chosen prey. This is different, however, when choosing a wildebeest. In this example, the lion's choice is not going to be the weakest of the animals, because the wildebeest do not present the kind of danger that the zebra do. In this case, the lion's actually going to want to pick the plumpest, juiciest, healthiest animal there is to upgrade its caloric intake. From the wildebeest's point of view, however, this is not a good idea, because no group wants to sacrifice its breeding males and females. They would rather offer up one of the diseased individuals. So the coloration of the wildebeest is such that the lion cannot keep a lock. This is a disruptive mechanism. Monochromatic things, as we saw earlier with the ruler and everything else, things that are monochromatic do not show up under delta vision. So the lion would be presented with a very confusing scene, and in no way could keep a lock on its chosen adult prey. This is the reason, by the way, that most prey animals are monochromatic, and most prey animals do not present much of a challenge to a lion anyway. Somebody pointed out, well, what about this? This is a very common marking in antelope. For example, the springbok on the top picture there has almost a set of 3 different colorations. It didn't take long to figure out what was going on, and the first clue is that these stripes run parallel to the direction of their motion, which means that they're essentially invisible to delta vision. However, these are pronking animals, and pronking is a behavior used by prey animals to show the lion that they are superior in agility and endurance. They can spend enough energy going vertical that the lion shouldn't even waste its time chasing it. And what happens now with these horizontal stripes moving in a vertical axis, the animal shows up extremely well. They want the lion to see it, which is also the reason that their rumps are distinctly colored as well. So it's either a black or a white rump in case the lion is coming from behind. Talking about behinds, one of the challenges and one of the mysteries of biology is why zebras and horses wag their tails when they're angry, whereas dogs do it when they're happy. And so, of course, I found some video of 2 zebra. Here we have a stallion on the right wagging its tail, flashing its tail, and the mare on the left standing very still on the left. If we run that through animal vision, this is what we get. The tail, as it moves across the rump, seems to be painting a nice, clear image of the size and strength of this animal's hindquarters. This is the killing end of a zebra, by the way. If you're a competitive stallion and you want to take on a zebra, the reason they flash their tails is to give you a very clear indication of what they're going to be up against. The mare, on the other hand, stands dead still, doesn't want to be involved, and is actually invisible in that scene. Dogs, on the other hand, the killing end is on the front. So they use their tails as a sort of a friendly gesture. And on these 3 images of true wild dogs, we have the dingo, the wolf, and the African wild dog, you'll notice their tails are bushier than they seem to need to be, and they're all tipped with a very distinctive end on the end. So it's obviously used as a visual signal to bring attention to their hindquarters, which is not threatening. This is a universal behavior that, again, has puzzled biologists. Why do insects, birds, people all cock their heads? And puppies. Oh, so cute. I believe the reason is pretty clear if we look at it through the lens of delta vision. Have a look at those mathematical symbols on the left. Now, if you're an animal and you're looking at a photograph, for example, everything I've said tells you they cannot see that photograph unless they're moving. But one way to see that photograph is to simply move one's head, which creates delta changes between frames. The other way to do it is to sort of nod your head, which you can do as well. The problem is, both the shaking and the nodding don't give you all the detail you're looking for. Those are two delta rendered versions, and you can see that the symbols have not been rendered properly at all. They look completely different, and not all the information's there. The only way to get it is to move your head in a 45-degree rotation at once, and then everything clicks into shape. So I believe that head cocking, which is associated with sort of quizzical behavior or even fear, is a result of this. If you go to a museum and you watch people in front of abstract paintings, you'll see a much higher frequency of this than you would if they're looking at something that's pretty obvious. And that's sort of a vestigial reflex that we have. Just one word of warning: do not. I learned this the hard way. Just keep your parental controls on. You'll be fine. I just want to run through a couple of animal behaviors that will help you maybe observe with your own pets, your cats and your dogs. This happens to my dog all the time. I throw the ball, the dog perfectly tracks the ball in the air, watches it land, sees it bounce, and retrieves it. If for some reason it misses that point where it hits the ground, and the ball comes to a standstill, the dog is actually looking all around. It's right there. And the dog's sniffing, so it tunes out its vision and starts using its scent to try and find it. I don't know if you've noticed it with your dog, but try it and you'll see it works. Feline stare-downs are very common behavior with cats, and I recommend if you have a cat, do this yourself. When the cat's sort of just sitting around, walk up to it and freeze. Your freezing behavior is not something your cat's used to you doing. And you'll actually be surprised how well you can freeze. Human beings have this ability to freeze extremely well. The cat is going to sense that something's up, and what's going to happen is it will freeze as well. And a protracted, kind of tense standoff will ensue. And what's happening is that you have disappeared from the cat's visual scene. So the cat actually, it knows you're there, because it smells you and it saw you earlier, but it cannot see you, which puts it at a disadvantage. And what it's hoping for and waiting for is for you to make the first move so it can paint a delta image of your position in its vision. And that standoff can go for a long time. The cat that moves first is naturally at a disadvantage. This is why you see lizard and small rodent locomotion that works like this. For this lizard to get from point A to point B, it actually does so in fits and starts. So it'll be stock still. And one thing that this being still allows it, remember it has almost 360-degree vision. By keeping absolutely still, it can very quickly detect motion in its environment. If it detects no motion, it will zip forward maybe 5 or 6 feet and freeze again. So this does two things. It allows them to check for predators, and also lowers the risk that a predator will see that movement on its way. Watch it with squirrels. I don't know if you have squirrels where you live, but you'll see that. I see it every day. If you ever want to get your dog some exercise and want to put it on a treadmill, it will balk if you put it on a standard treadmill. Their visual system cannot pick up the changes that occur in a black base. Paint some stripes on it, and the dog will take to it very quickly. If you ever want to catch flies, what our instinct for most people is to sort of move as fast as we can to hit the fly. It's completely the opposite, because the fly easily picks up that motion at 300 frames a second. What you can do is you can actually fly underneath the animal's visual radar, and if you move it at about an inch a second, the fly cannot pick up those delta changes. So the fly will just sit there until you're about an inch away. You can grab it and, I guess, eat it if you want. I'm starting to wonder if we shouldn't try and explain conventionally understood behaviors in a new light. And one of them that comes up is blinking. There's something about blinking that's not quite self-evident. We know that it's a process of protecting our eyes and lubricating our eyes. But there's something more to it. Some research recently has shown that people tend to synchronize their blinking rates. We do so in movies. People will tend to blink altogether at the end of a scene, or perhaps at the end of a speaker's sentence. So something is going on there. Also, animals will blink more in the presence of predators than they would otherwise. Now, I believe that one of the after effects of a blink is essentially a complete visual refresh. If you're an animal and I'm looking at this crowd, all I can see are those people that are moving their hands and legs, but I can't see anything about the auditorium. If, however, I blink and open my eyes, I refresh my visual field completely. So I briefly get a complete picture of what's going on. Human beings blink so much, in fact, that we spend about 5 to 10% of our day with our eyes closed because of blinking. So the question is, well, why don't we have a clear nictitating membrane like this bird? That way we could keep our eyes open all the time. In fact, birds not only have nictitating membranes, but they also have eyelids. So they both blink and nictitate at the same time. And the only reason that I can think of is to do this refresh. Just to kind of give you an idea what the refresh does, if you look at these two iguanas from the point of view of a predator, a blink would create a full refresh that you see on the left. It's a complex visual scene. So it's now it's up to your cortex to try and figure out the shapes and actually what's going on. Whereas if those animals had moved, you would see a much easier, clearer vision. So blinking is not a perfect solution, but it's better than nothing. And finally, I was wondering if maybe there's some more vestigial artifacts in our own vision that harkens back to our evolutionary animal past. And I came across this experiment done in the 1950s, where Dr. Pritchard had attached a tiny projector to the surface of a woman's eye and was projecting an image directly onto her retina. And what this allowed him to do was stabilize that image onto her retina. So even as her eye moved, the little saccades in her eye sort of wobble back and forth, the image was fixated on particular cells. And she reported seeing this image of a cat for about 2-3 seconds and then saying, "You've turned it off," when in fact he hadn't. So the fact that the retina turned off the visual impulses after about 2-3 seconds, at least in some way, indicates that maybe our own visual system is fundamentally grounded in that animal behavior. Brain damaged patients, whether through stroke or car accident, neurologists report that when somebody's visual cortex is severely damaged, so much so that they're blind, they almost always retain the ability to see motion. So I found this quite interesting because here we're dealing almost with an animal visual system. You cannot see anything except things in motion. So I'm hoping that some more research will be done with those patients to see if we can piece together how the world would look if you were a cat or a dog. And finally, some of the big biological questions. The explosion in cranial size over the last 5 million years. This is the granddaddy of all biological issues. What triggered this? We're not sure. I don't believe we will find the answer unless we consider that vision played a big role in this, because vision takes up so much of our own brain power and modern human vision gives us so many advantages that it could have easily sparked an arms race amongst early hominids to trigger the increase in brain size and visual cortex. So human vision gives us the ability to make tools, to read books, and essentially see into the future. We can look at a scene like this and imagine around the corner there's a verdant valley with a lake that will help us. So the advantage of human vision cannot be underestimated, and I believe that so many aspects of biology have to be reconsidered in that light. And now the best part of this is that I get to take your questions and to hear your challenges to the theory. And I thank you very much for listening, and thank you.
excellent talk, and we definitely have time for questions, so please use the mic.
Hi.
It looks like some birds and animals can see their images in the mirror, while others cannot. Do you have any explanation of this difference?
Sure. I'm not quite sure okay. All animals can see themselves in the mirror to the extent that movement would trigger vision. I think what you're pointing out is that animals can recognize themselves in the mirror. The ability to sort of look into the mirror and be self-aware that what they're looking at is themselves. That's pretty much reserved for the higher end of you have to have a bigger brain in order to pull that off. Chimpanzees, dolphins, obviously humans can do it. Whereas dogs and cats see another dog, but they're not self-aware. But in terms of vision, looking at a mirror would be no different from looking at another dog. The dog will see movement, and it should register in its brain. Is that your question?
More or less, but there is a different thing that, for example, cats can watch TV, while dogs cannot. Parrots can also watch moving images, but other animals cannot. So I mean, not only the image in the mirror, but also the flat image.
Right. The issue of TV is kind of an interesting one, and it actually has a lot to do with flicker fusion rate. The fact that animals with a high flicker fusion rate would watch TV, they would actually see a very flickering image. They would see it, but it would flicker on and off, be quite annoying actually. And my cat and dog both do watch TV, but only occasionally, and when certain movements are on the screen, for example, fast-moving other dogs, they can pick up that sort of motion, but they seem very disinterested in everything else, and I think the reason for that is the difference in flicker fusion rate. Thank you.
Over there, on that mic.
Hi.
Hi. I was wondering if a predator is looking at a frozen deer, for example, couldn't they just cock their head and see the outline? You did something similar with iguanas, but it seems to me that a simple head cock would quickly illuminate the shape or the outline of the deer.
They could, but they don't. Imagine, sort of try and put yourself from a predator's point of view. The predator is aware that that prey animal is there. So it smelled it, which brought it to that environment in the first place. It has now frozen itself and is watching the prey animal for movement. Now the prey animal is unaware that the lion is there, so its movements are a little more careless than they otherwise would be. The lion has no reason to cock its head and potentially give away its position, because that head cock, unfortunately, creates movement, which, because this animal has almost 360-degree view, would pick up immediately. Animals are extremely sensitive to movement. If you have a cat, you can sit there with a cat, the cat's lolling around, you wiggle your hand, the cat's right on it. It's because that's all they can see. So a lion cocking its head is definitely going to give away its position. So they could, but they don't for that reason.
And how might you go about proving this hypothesis?
Well, that's an excellent question. I was hoping you could give me the answer. One of the things in proving, you don't really prove a hypothesis, I guess. You can only disprove it. But some indications that you're on the right track would be that it can make predictions. And although I didn't mention it at the time, that issue of that red-banded snake and trying to explain its coloration was actually a prediction on my part. At the time I was pondering this, I didn't know that birds of prey could only see in the green end of the spectrum. But I looked at this and I said to my assistant at the time, I said, I bet you that birds of prey can only see in the green end of the spectrum. And he says, well, why? I said, because it's the only thing that could explain this particular coloration. It makes no sense otherwise. And this is before the internet was around, so I had to pull out all my animal books and start leafing through. And sure enough, the prediction was true. So I think, and there've been a couple of other examples of that, So making predictions that tend to be true is a definite sign you're right. The real crux, the real only way to prove it is to actually climb inside an animal's head. And I don't say that facetiously. There've been an enormous amount of studies done on animal vision, but none of them can really recreate the image that we see in our head. It's a very personal thing. So all we can do is do experiments, look at animal behavior, and try and explain it through another mechanism. For example, the zebra stripes, there really is no satisfying explanation. I really have not found anything, and I've done a lot of research on it. Everyone's kind of beating around the bush that somehow they're trying to confuse the lion, when in fact, from my perspective, the only explanation is in the light of delta vision. So whether that's proof or not, we'll see. A lot more research will have to be done, and I hope to get this published so that other researchers can take a stab at it. Thank you. Hi.
Yeah, coming back to the zebra, I just want to see if I sort of get the punchline. You're basically arguing that the zebra has evolved in such a way that, in fact, it's clearly obvious to the lion. It's not trying to not be seen by the lion,
Right.
and maybe it's willing to do that because it's such a strong animal. What does it gain from that? Is the idea that the weaker zebra might move more slowly and for some reason be more visible to the lion, and this is a way of, weeding out the weak?
Yeah, I think every herd animal species out there has an interest in preserving its healthy members and has an interest in giving up. They have to make a sacrifice. Somebody's going to get eaten. They would much rather sacrifice a diseased animal, for example, cull the herd, strengthen the herd. So there's an evolutionary reason to start evolving this mechanism. All animals do it. It's just that each one uses slightly different strategy depending on their own physical makeup compared to the predator. So you can imagine a situation where zebras didn't have those stripes. Lions would be much higher, much more likely to attack a healthy breeding male than not. So I guess what I was trying to say in this is that because every animal species wants to protect their healthy individuals, the zebras have found out that since the lion targets a weak individual to begin with, you might as well shine the spotlight on that animal and everyone else can get away. It's kind of like this. This is a true story, and you've probably heard something similar to this. Some friends of mine were hiking in Alaska. They were told that there were bears in the area. They had to be careful. And the four of them were walking along, and two of them sort of snuck out ahead and hid behind a rock. And the other two were walking along, and these two jumped out and roared. And of course, they started to run as fast as they could. And my one friend said that at the time he was going, why am I running? The bear can run 4 times faster than me, but why am I turning the back on the bear? And really what was going on, he wasn't trying to outrun the bear, he was trying to outrun the guy next to him. And he couldn't help himself. And that's the case with the zebra. And if the zebra can run, they don't have to run faster than the lion. They simply have to run faster than the guy next to him is slower. And this is one way to allow the lion to find that guy. So it's in everyone's interest, except, of course, the diseased individual. But somebody's going to get hurt. So I hope that answers the question.
Thanks.
Thank you.
Do we have any questions in Boulder or Charleston? Not at this time? Okay.
When I was a child and would draw a picture, I know I had the habit of pausing now and then and looking at the drawing and turning it around a few times on the tabletop and then going back to drawing. Now that certainly does seem idiosyncratic, but can you think of some rationale based on your findings why that might help me study the picture, might have helped someone study a picture that they're drawing by twirling it around?
No. I'm sorry.
So you're making this distinction between human and animal vision. You're making kind of a strong distinction, and you're calling the evidence that we also do change detection vestigial. And I wonder if it might make more sense to say, no, our eyes, the early visual system where the processing happens in the retina, behind the retina, it's the same. There's no reason to believe from what you've presented that there's any difference there. And then it's the story that our brain makes up for us after that constructs the scene that's different.
Absolutely, you hit the nail on the head. In fact, we know that the retina is part of the brain, and some processing is done there. Some filtering, some color correction, and things like that. And I agree with you that there's no reason to believe that our retinal vision is any different from animals. And it is in our visual cortex, which is larger than animals' brains, that all this additional calculation takes place. So yes, and I think part of that brain damage issue is when we damage that, we're sort of back to what seems to match up with animals. So and you're absolutely correct on that.
Thanks.
Thank you.
You said in the context of your delta vision that the larger frame rates for species that have smaller brain masses begins to make more sense because the amount of data is smaller.
Yes.
Does it scale with brain mass?
No. It scales with species. It's not true to say that the bigger your brain, the slower your frame rate. And the reason is there's a microscopic bacterium called the capillia. It's actually a beautiful little animal. It's translucent, so we can actually see its visual scans taking place. And it scans about once every half a second. So its frame rate is even less than ours. So the reason that this doesn't overwhelm its visual system is because all it's really looking for is changes in light and dark. There's not much it can do to get away from anything. It's just basically looking for slight movements to maybe evade. So it's very species specific, and animals that operate in high-speed environments tend to have higher frame rates. Animals that, like a tortoise that doesn't need to operate in that environment, will tend to have a slower frame rate. So it's not brain dependent, it's more behavioral and ecologically dependent.
Sorry, are you talking about the frame rate or the amount of data? I'm talking about the amount of data that's collected.
Okay, I beg your pardon.
And although your point about that other species, which I have no idea about, is that
Right, no, the amount of data is dependent on frame rate. The higher the frame rate, the less data. There's a complete correlation between the two. Thanks.
I'm curious about you mentioned that human vision is different, and one thing that I think about is the way that we tend to flick our eyes around in a visual field, and that leads to the thought of REM sleep, dreaming, and image creation, that when our minds are most active while asleep, our bodies still flicker the eyes around even though they're closed. Do you find that has any correlation based on your research?
That's a good question. It's my understanding that animals will also have REM sleep. So while, and honestly, I haven't given this much thought, but I suspect you're right, that there's some mechanism in the brain that's connected to eye movement, to thought patterns. It makes sense. Just one thing on this sort of eye flickering, in terms of vestigial things, when we scan the room, if I scan the room from left to right, I don't do it in a fluid motion. I use a series of saccades, which are like sharp ballistic movements that, so if you slow down my vision, you'll see I'm looking boom, boom, very much like reptilian movement. Our own brains can't really handle this kind of fast movement. So eye movement and visual representation are inextricably linked, and we're not quite sure why yet, though. Thank you.
Thank you very much. Let's give